Welcome, everyone, to today's conversation. We're going to focus on the real deep foundational questions of physics, questions regarding how to really make sense of quantum mechanics, a question that we can't fully address as yet, questions that speak to the nature of time. Can we gain insight into the distinction between past and future in a physical framework that we've discussed in this program before? The physics, the mathematics seems to treat forward in time and backward in time on equal footing. So can we get a handle on where this deep asymmetry in human experience comes from? So the kinds of questions that really speak to the way in which physics tries to really explain the world, both in terms of the experimental data, but also to explain the world in terms of human experience, which ultimately is what the core of the whole project of physics is all about. And to discuss these deep issues in physics, I'm so pleased to have someone who's had a deep impact on these questions worldwide, but has also had a deep impact on my own thinking about these questions. And that is David Albert, who is the Frederick E. Woodbridge Professor of Philosophy here at Columbia University in New York, where he directs the MA program in the Philosophical Foundations of Physics. So welcome, David. It is so great to see you.
Thank you, Brian.
I
You also direct the MA program in
I know
Philosophy Foundation.
as I read that introduction, I was like, I wonder if I could shoehorn myself into that too. But yes, since I'm newly in that
Right.
position, it hasn't yet fully sunk in, apparently. And partly I felt like we should have this conversation at the place where too infrequently we meet when we discuss these kinds of issues, the Hungarian pastry shop here
hmm
in New York
hmm
City. But this is probably a somewhat quieter, more contemplative place for us to have this conversation. So thank you for joining us. So what I'd like to do is begin with a story, a very, very short story, but it's one that happened in the late 1990s, I think, where I was just newly at Columbia and I was asked to give a talk at Rutgers in the philosophical foundations of physics type of gathering that they have there. And I was giving a talk on work that we had recently done on trying to understand this quality of string theory in which you could have multiple different geometrical forms for the extra dimensions of string theory, and yet they could give rise to exactly the same physics, this phenomenon called mirror symmetry that I was involved in discovering, as well as other people like Ronan Plusser, Kuman Vafra, Nicholas Warner, many others as well, Philip Candelas. And after the talk, Shelley Goldstein, who anybody in the Philosophical Foundation of Physics knows well, Shelley Goldstein came over to me in a very nice, supportive, avuncular way and said to me, physicists need to think more fully about ontology. And I have to admit, there's a chance that I, 30 years ago, did not know what the word ontology meant, in the context of these ideas. But since then, I've become to really deeply appreciate the need to investigate and think through and really test our understanding of what's real. What of our mathematics is actually telling us something real about the world, the ontology, the commitment to the things that make up the furniture of reality. And so I think that's a theme that will naturally have a place in all that we discuss here today. But where would you place the issue of ontology in the hierarchy of essential questions that we need to really address in order to have physics describe the real world?
Well, maybe it's worth backing up a little bit. As of the end of the 19th century, around the end of the 19th century, um, more and more people seem to feel, because of the sort of spectacularly impressive success of the project of physics up to that time, that physics was sort of the royal road to what people used to call metaphysics. That physics, that the right place to read off your metaphysics, the right place to read off your picture of what the world was really like, was to attend to, and as you say, what the fundamental furniture of the universe is, was to attend to what physics was telling you about that. And, I remember that what excited me when I was in junior high school, for example, about the theory of relativity, particularly, I guess, special relativity in this case, was this astonishing realization that what had seemed like philosophical questions. You say, "Gee, I'm curious about the structure of space and time. I wonder what experiments I might be able to do in order to shed light on that." And a very reasonable initial reaction, and this was certainly the reaction of people like Kant and all sorts of people in the philosophical tradition, that's not something you can do experiments to find out about, because you can't, any experiment you're going to do is itself going to be within space and time. There isn't any possibility of stepping outside of space and time to look at what their structure is. So you shouldn't hope for the possibility of doing experiments or doing observations that are going to that are going to be able to somehow shed light on things like the structure of space and time themselves. They come before, they have to be in place before anybody even starts talking about an experiment. And all of a sudden, Einstein is able to show you how, if you're clever enough, you can trick these things into exposing features of themselves to observation, notwithstanding that, of course, everything you do in carrying out this observation occurs within space and time and against the background of space and time in the first place. So I remember being just floored by that. And like I say, sometime when I was in junior high school, and that experience of being floored by that very much was very formative of the way in which I was interested in physics ever since. That it was this way of pursuing what were essentially philosophical interests about the deepest aspects of the structure of the world, but pursuing them in a way where you weren't going to go back and forth for thousands of years in debates in people's bathtubs. And there was actually this thrilling possibility of learning something in the way that scientists learn things about these things that had seemed beyond the reach of anything like scientific investigation. So, what was exciting to me about physics was this idea that you could use it to sort of stage raids on what had traditionally been philosophical territory and come back with these astounding treasures. Okay, enough autobiography. I think physics was very much in a mood like that at the end of the 19th century, that we had really found, in some sense, the right way to do philosophy, or at least the right way to do metaphysics, and that's to do fundamental physics. Um, and what was interesting and what came to fascinate me a little bit later is that there was a sense in which all of that was declared to have collapsed. Those kinds of hopes were declared to have collapsed with the advent of quantum mechanics. That what was that the kinds of phenomena we were running into in quantum mechanics were, I don't know whose quote this is, but it's a cute one, not merely stranger than we knew, but stranger than we could know. Stranger than the human imagination, the scientific imagination is ever going to be able to fully penetrate. And you had figures, the founders of quantum mechanics, figures like Bohr and Heisenberg and Born and the people around them, who thought that what had been discovered only a little later than special relativity, what had been discovered about the structure of matter at the smallest scales, showed that these hopes to sort of that physics was going to be something from which we could read off our metaphysics, that physics was going to be something from which we could learn in a really genuinely philosophically satisfying way what the world was like. These kinds of aspirations for physics were declared to be naive by the founders of quantum mechanics. That's not what you could expect from physics. Your expectations from physics had to be much, much, much more modest than that. That you were going to be given algorithms which would enable you to predict the outcomes of certain experiments or something like that. But the deeper speculations about why those experiments came out that way and what was going on in between the beginning of the experiment and the end of the experiment, what was going on under the table. It was naive to imagine that physics was going to be able to answer questions like that. It was a kind of hubris to imagine that the human scientific imagination was going to be able to penetrate arbitrarily far down into the deep structure of nature. And
But if we can just pursue that for 1 second before we
yeah,
run out. So I presume you're referring, at least in part, to Niels Bohr,
I am. Yes,
who famously took the helm of the quantum explorations and basically shook people by the collar and said, "Stop asking those kinds of naive questions
right,
that you're used to from your classical intuition
right,
regarding how nature actually is."
right,
Best we can ever do in physics, and the only thing we should expect of a physicist, is to make predictions for what we will see in our instruments
right.
when we do measurements. And so, what kind of impact do you think that had on?
I mean, as a historical matter, it was, I think, a quite astonishingly long episode in the history of science. One that I don't think has yet really begun to be explored in the depth it deserves by historians of ideas and historians of science. But there really was a pretty dogmatic um, and pretty brutally enforced insistence that these were not proper questions.
When you say brutally enforced, I mean people were kind of ruined.
People's careers were destroyed.
Yeah.
People's careers were destroyed, very simply and straightforwardly. And this happened over generations. I mean, this happened in various ways, dating from the 1920s, I would say, through to the 1980s or 90s. It was a very long episode. It took many forms. I mean, it's a really interesting historical period. For example, in the 1950s, in the case of people like David Bohm, this insistence that people not ask these questions got tied up with the whole apparatus of McCarthyism
Yeah.
in the United States. And that's an interesting episode. Earlier on, I think, I mean, this is pure speculation, but I have this intimation that a lot of these pronouncements on the part of people like Bohr had to do with a kind of zeitgeist that was in the air at the time that had to do with various forms of modernism in art and in literature and so on and so forth. I think Bohr, had something in mind like saying to the modernists, you think you've got a crisis of representation? Okay. We don't have a crisis of representation just about human motivations or something. We got a crisis of representation about rocks. Okay. That's infinitely more radical than your crisis of representation. And so at various times, this played into the historical moment in various different ways. And some of them were interesting, philosophically interesting, and so on. And others were just silly and dogmatic and often brutal, unlike we've been saying.
And we should add, though, there are still many in the physics community who hold
Yeah.
to the perspective that Bohr laid down. So it's not as though we all uniformly look back at
Right.
that period
Right.
as a time when there was unnecessary suppression of a
Right.
certain kind of curiosity.
Right.
But it's also worth, on the other hand, to note, I think Bohr's view was not that the approach that he was putting forward with many other colleagues was somehow meant to suppress certain kinds of questions. It was more a profound, radical, philosophical change
Yes.
of what we were supposed to expect from the investigation and the whole project of physics,
I
right?
agree. I agree. No, I mean, they saw themselves as the vanguard of an enormous, earth-shaking, broad intellectual revolution. Yeah. And this was connected in this was connected, as far as I know, in Bohr's mind with the work from a generation before his of his countryman Kierkegaard, and also of people like Hegel, who's that was part of the kind of philosophical education that Europeans like Bohr received and very much absorbed. Yeah, there were a lot of very deep philosophical questions engaged here, and the idea of what's come to be called a sort of old-fashioned, flat-footed scientific realism. Okay, that the aspiration of science ought to be to tell us literally and straightforwardly what the world is really like. This was regarded as hopelessly and laughably naive, okay,
Right,
at
right.
the time. Exactly what had excited, a junior high school David Albert about Einstein. That was the very picture of what Bohr and his circle thought to have been revealed as hopelessly and laughably naive as a set of hopes for what science might give us.
And how convinced are you now that that was the wrong way of going
Oh,
about
I
this?
mean, completely convinced. I mean, we may end up. Maybe we'll get to talk about this. There are all kinds of questions about where we might end up. Okay, um, but the idea that Bohr thought he had arguments. These arguments are not easy to reconstruct now in hindsight. When you try to do them, it just sort of falls apart in your hands. But it had something to do, Bohr had some idea like, well, there's the following tension at the heart of the whole scientific project. On the one hand, he thought we absolutely need to describe our experimental results and to communicate our experimental results and to reason about our experimental results in what he called classical language. This was inescapable. Why it was inescapable, I was never sure. Is there some reason why we can't learn the quantum mechanical language? I don't know. Bohr thought this is a very deep fact about the way science not only proceeds but must proceed. And at the same time, this classical language had been revealed as inadequate for the description of subatomic phenomena. Okay. Um, and like I say, for reasons that I don't understand, there was no option of going native. There was no option of learning the quantum mechanical language. You were stuck in the classical language in reasoning about your experiments. And Bohr thought that the minute you saw this predicament, if you had any intelligence at all, you would see that this old hope of a sort of straightforward, naive, literal, realistic description of the world coming out of science was just hopeless.
Mhm.
Okay. That there was a tension between what you needed on the experimental level and what was emerging on the subatomic level. That wasn't a tension that you could hope to cure or resolve. It was a tension that once you saw it, you needed to simply accept. Okay. And that was it. I haven't really constructed much of an argument there. I don't know exactly what the argument was, but it involved
Sure.
locutions like that. Okay. And this was somehow very, very influential. And anybody who grew up in a physics education during the era that you and I grew up in physics educations knows very well that if you raised your hand in class and said, I don't understand this in a deep sense, you were told you're not supposed to understand it. And if you want to know why you're not supposed to understand it, go read Bohr's response to the EPR paper. And if you do go and read Bohr's response to the EPR paper, it's gibberish.
Yeah.
Okay, it's like listening to the Oracle at Delphi, or it's really hard to figure out what the guy is trying to say. But every physics professor will tell you that's where it's resolved. And if you ask the physics professor, could you just tell me what his main point is? The professor would say, go read the article. And you know, you went to read the article. I heard the following rumor. I don't know if it's true. I don't want to vouch for its being true, but someone told me that the sort of canonical version of this Bohr paper that was published in all the main collections and so on, that was borrowed from collection to collection over the course of a period of like 60 years, turned out on closer examination to have the pages out of order, that there were two pages whose order was reversed. And no one ever noticed, okay? No one ever noticed, okay? And so
An argument so good that you could interchange and it still works.
right, exactly.
And again, just to underscore your point that it's not metaphorical or poetic. I mean, when I took quantum mechanics, I took it with Norman Ramsey, who won the Nobel Prize.
Right,
And I was the kind of kid who, when I didn't understand something, I would go to every office hour
right,
and like harangue the
right,
professor,
right,
which I'm sure became irritating,
right,
little doubt about that. But I peppered Norman Ramsey with question after question of like, when you do the measurement, what are the other
right, right,
possibly, all the things that we
right.
now still struggle with. And he valiantly tried to respond, but in the end, it came down to versions of, read some of the papers of the founders,
Right,
because
right,
that's where our understanding is. But we should also stress, of course, that quantum mechanics was doing such a spectacular
right.
job at the
Unbelievable.
job that Bohr set it as its primary purpose, namely
Right,
to explain the results in experiments,
right.
that I think people were willing to say, somewhere out there are answers to these deep questions.
Right.
But right now, we just want to use this theory to predict the spectrum of hydrogen and helium, to understand magnetic moments of particles and scattering
And
amplitude.
to change everyday life on Earth,
Yeah.
which it did
Yeah.
hugely. No, I couldn't agree with you more, and that's a very important point to stress.
Yeah.
And no doubt, this bizarre intellectual situation would not have survived nearly as long as it did if not for the really spectacular empirical success of quantum mechanics. That's right.
Yeah, absolutely. And so one way of framing the tension that you described between Bohr's stipulation of using classical language and talking about equipment and measurements, and using the quantum formalism when actually analyzing the subatomic particles, one way of framing that tension is, as you said, why can't you use the quantum language to describe the equipment? After all,
Right.
the equipment is made of the particles, the very
Right.
same stuff that you're using in the subatomic realm, the
Right.
quantum formalism to describe. It's just a lot of those particles put
Right.
together. And
Right.
the person and the brain also made of the same ingredients, it's just in some
Exactly.
configuration. So
Right.
isn't it all quantum mechanics all the way through?
Right. Right.
And I think certainly that's the view that has taken over.
I think that's right. And I mean, this relates back to the question you asked a few minutes ago. How convinced am I that Bohr was wrong about all this? Um, yeah, I'm 100% convinced that Bohr was wrong about all this. We do now have explicit, well worked out models, at least in the case of non relativistic quantum mechanics. There may be questions in the relativistic case, so on and so forth. But at least for the cases that Bohr was focusing on, We have explicitly worked out models about how to go native in this way, okay? How to use the quantum mechanical formalism to describe everything, including us making our measurements, including us having this conversation, blah, blah, blah. Um, so, so Bohr has just been shown to be wrong in that way in what they call in mathematics a straightforward constructive proof, okay, a straightforward constructive counterexample. We've got them, okay. um, there are issues now about, gee, if we end up with several of them, which we do have on the table now, and they all, and say two or more of them turn out to be empirically equivalent to one another, there's no experiment that might be able to distinguish between them, then um, if that's the way it works out, and we're many, many years from knowing if that's the way it's going to work out, if that is the way it works out, that's going to be a disappointment of a different kind. Okay. It's not that we can't have even one picture of what's going on under the table, but we have too many. Once upon a time, this is a worry that philosophers refer to as underdetermination of theory by experiment. Once upon a time, people in philosophy of science who wanted to dismiss this worry as not very important used to give people lectures like, your problem is you never really got your hands dirty with actual scientific work. And if you had, you would know that the problem is not that we have too many empirically adequate theories. The problem is to get even one. Okay. And the idea that you're worried about us having too many is just silly and historically unsupported. In foundations of quantum mechanics, it is beginning to look like there may be a
Yeah.
worry like that, and or at least one can imagine future scenarios in which there turns out to be a worry like that.
And can
So,
we drill down on that worry a little bit
sure,
further?
sure,
Because I ultimately do want to get to the specifics of the quantum measurement problem, which you were
right,
alluding to
right,
in these theories that are on the table right now. But before we get there, the reason why I want to drill down a little bit further on the underdetermination issue is because one of the most powerful realizations in arenas like string theory and unified theories of the last 20, maybe 30 years or so, has been this recognition of what we call duality.
right,
And,
right.
and that, in some sense, is an
Yes,
underdetermination of a sort,
yes,
because much as in my story that I told at the outset, where we had two different forms for the extra dimensions, one theory, we now have many examples in
right,
string theory of two radically different mathematical formulations that we believe we can't prove yet. But we believe, because the evidence mathematically is so powerful, that they are absolutely physically indistinguishable,
yes,
literally
yeah,
indistinguishable,
yeah,
and yet the mathematical formulations are so different. And I have to say, this has had a indirect profound impact on me, because in the early years, like when we first began to talk about these sorts of things back in the 1990s, I had a very, I think, naive view that what we physicists were working on, the mathematics was like, it was out there. It was like, it was reality. Like there was no
right,
difference in my mind, I
right,
think, between reality and the equations that we were fiddling with. The equations might be wrong, in which case they were the wrong description of reality. But if they were right, they were kind of reality, isomorphic to it. But with all these dualities and other considerations too, I've come to a view that I think is a minority opinion in the physics community, that what we physicists do is we develop these narratives, these mathematical narratives that give our best model of some aspect of physical reality. And so that's it. And so rather than the model and the narrative being reality, it's a story we tell about reality. It's predictive. It's not just made up out of a whole
right,
cloth.
right,
Have incredible restrictions on it and very powerful implications of those stories, because they can tell us about things that we've yet to encounter.
right,
That's a beautiful quality of these
sure.
particular kind of stories. But given that view, I'm not surprised that there could be multiple narratives, describing the physical world. How do you think about?
Hey, look, I think, I mean, as I just indicated, it's something that I'm not sure what to think about and that I worry about. I mean, let's take a very simple example. Talk about classical mechanics. Multiple particles floating around in a three-dimensional space, which is the subject of Newtonian mechanics. Um, you know, some of our audience may have heard that there are all kinds of mathematical objects that we use to represent such a set of particles, which are convenient in many cases. In the 19th century, for example, it was discovered that it was very convenient and led to very beautiful pieces of mathematics to talk, instead of talking about three-dimensional space with n particles floating around in it, to talk about something that they called phase space, which was a six, which had 6n dimensions, where n is the number of particles you're talking about, so that a single point in this phase space would pick out for a set of n particles what each of their positions were and what each of their momenta were. And it turns out that if you look at the evolution of this system in phase space rather than in ordinary three-dimensional space, it suggests all kinds of beautiful mathematical shortcuts and deep understandings of the mathematical structure of what's going on, so on and so forth. So look, take an example like that. The phase space representation is, to use the word you used, completely isomorphic to the three-dimensional representation. So suppose you're an instructor teaching a class on analytical mechanics, and a student comes, and you talk about phase space, and a student comes up to you after class. Actually, let's imagine two students. Student number one: wow, professor, you changed my life today. You really blew my mind today. Professor says, what do you have in mind? Student says, I now realize, I thought all my life that we lived in a three-dimensional space, and it turns out we live in this 6n dimensional space. It just completely blows my mind. Thank you, you've changed my life. I mean, I'm never going to be the same. I think most people would say the professor ought to say to him, no, you have a misunderstanding here. This high dimensional space is a convenient mathematical device. In some sense, it's not to be taken seriously as a picture of what the world is like. And the student says, I don't understand. Well, okay, that's the first student. Student number two comes and says, Professor, you completely blew my mind today. I'm never going to be the same. I now realize that there isn't even such a thing as a question about whether we live in a three-dimensional space or in a 6n dimensional space, because the two models are completely mathematically isomorphic. Okay, it's not saying a different thing to say that we live in a three-dimensional space and we live in a 6n dimensional space. I guess I think, but this is a big old topic of discussion in philosophy of science. I guess I think that the right thing to say to that student as well is, no, you're missing something important here. Okay, it's true that there's a mathematical isomorphism between certain aspects of these two models, but that doesn't mean that it's meaningless to ask whether we live in a three-dimensional space or a 6n dimensional space. The student says, but why? Both of them are empirically equivalent to one another. What possible reason could there be to prefer one of these claims as the realistic description of the world to the other? And there are a lot of responses that a professor may have to a question like that. Whether any of them are adequate, I'm not sure. But here's how I can imagine responding. I say, look, there's something you don't understand about the nature of scientific inquiry. First of all, given any set of data, there'll always be an infinite number of theories, most of them completely wacky, that are consistent with this data. Okay. The planets are moving the way they do because angels are carrying them around who intend to deceive you about the actual laws of physics. Blah, blah, blah. This is just old fashioned philosophical skepticism. There'll always be an infinite number of theories that explain any finite body of data. That's just a simple logical truth. So there's always a question: why do we choose some of these theories as opposed to others at each step of the way? And I think one of the elements is something like this. We start, people in philosophy often speak of what they call a manifest image of the world. Okay. This is of course, there's no literal such thing, but what you have in mind here, it's something like talking about the state of nature when you talk about political philosophy, or what the world was like before there were any social organization. Here you talk about how the world looks to you prior to any serious scientific investigation or philosophical reflection. So, for example, it looks like the tables and chairs around you are solid objects that continuously fill the space they take up, rather than being 90% empty space or 99.999% empty space as we think now. Blah, blah, blah. There is this mythical object called the manifest image of the world. And the simple story about science is you start with the manifest image of the world. You have a sort of naive trust in the reports of your senses, so on. And slowly there turn out to be tensions in this manifest image. Here's a beautiful example. You put a pencil in a glass of water, okay? You get a conflict between two kinds of sensory reports. You look at the pencil, it appears to be bent in the glass of water. You run your finger along the pencil, it doesn't feel like it's bent in the glass of water. Oh my God, we've got a tension in the manifest image. Okay, we got to do something about this. What do you do about this? Well, you develop a theory of optics. You develop a theory of refraction, which explains to you why the pencil would look bent and not feel bent. And it turns out in this case, your tactile sensations were more reliable than your visual sensations. And now, what you got, what's going on now after this first step is called science. Okay. And you keep on rolling with this and you discover more tensions and you fix them up and you discover more tensions, blah, blah, blah. And if everything works out, long after all of us are dead, this scientific project gets finished. Okay. This scientific project gets to a place of what philosophers refer to as reflective equilibrium. Okay. That is, you get to a place where these tensions don't keep arising again and again everywhere you look. But one of the things you want to be able to do once this story is over, I take it, is to explain to anybody who wants to ask how it is you got exactly from the manifest image to the finished scientific image of the world. And one of the things I take it you want to be able to say for yourself is that you only relinquished features of the manifest image when you were forced to by the data. Okay. When you were forced to, you didn't make any gratuitous jumps. Okay. You didn't say, you know what, I decided now I'm going to believe that the moon is made of green cheese. Why? I like it. Okay. You didn't do that. Okay. What you had to start with was the manifest image. You took a whole bunch of steps away from the manifest image. But each of those steps, if they were conducted in accord with good scientific practice, was a step that there was serious pressure on you to take from the data. Okay. You didn't do any of it gratuitously. Okay.
Right.
So there is, I think, a good scientific principle, a valid scientific principle of scientific inference, which I would call, I guess, a principle of conservatism or something like that. You don't take another step away from the manifest image without having been forced to. You don't take a step away from the manifest image with just for the fun of it, because if you do that, science is no longer exciting. If Brian Greene comes to you and says we've discovered that time is going sideways and so on and so forth, you want to know that Brian Greene is talking about cognitive decisions that people had good reason to make. Otherwise, it's not exciting.
Yeah.
Okay. Good. So there is this kind of principle of conservatism.
And that's what you tell, presumably, to these students
After you
who,
tell to these students, no, you're wrong. Okay, you're wrong. The possibility of representing this in phase space does not mean that it's not possible to represent it in three-dimensional space, which is the more conservative thing to do. We haven't been forced away from that representation yet. Okay, if we haven't been forced away from it, we shouldn't take seriously. We shouldn't take this high dimensional space metaphysically seriously. Right, exactly right.
but that does suggest that, I mean, again, I don't want to get too sci-fi off the rails here, but if there's another intelligence that has radically different sensory apparatus,
Yeah,
conceivably their manifest image, if that's the correct terminology,
right.
will be so different from ours that their scientific trajectory might lead them to phase
That's
space.
that's a really interesting question. You could elaborate that question further. I'm not sure. This is probably the last step I'll be able to take in this elaboration at the moment. But yeah, I think that is a good question. That might get you very worried that science is more culture specific or more creature specific or something like that than we would like it to be. On the other hand, it might be that from the science we have, we might be able to make an argument that for any other alien civilization that we're capable of even recognizing as a civilization, recognizing as inquiring into nature, so on and so forth, there's a limit to how different their manifest image could be. A limit that's just imposed by things like natural selection, okay, and so on and so forth. So I don't know if you could make an argument like that in detail, but what you're saying is a really good question. Maybe there's something calming to say about it, maybe there's not. But
Right.
the worry when you get to things like string theory, or even when you get to things like the foundations of quantum mechanics, is that we have already gone so far from the manifest image that it's no longer clear what the conservative choice is. Okay. All the choices are completely wacky relative to the manifest image where we started. So it may be that when you go deep enough, this principle of conservatism loses its grip, okay, loses its ability to lead you, okay,
Yeah.
and and in that case, I think that's a new and interesting worry about a different way in which science might fail to realize its original naively realist
Yeah.
aspirations. Yeah,
Yeah.
I agree
Yeah.
with that. And I think that's a worry both about how wacky things are getting in foundations of quantum mechanics and about how wacky they're getting in places like string
Yeah.
theory.
So I'd love to turn to the quantum mechanics a little bit more fully, but I
Right.
can't help but quickly noting that I'd love those two students to come to my next class in analytic mechanics, where I teach them Hamilton-Jacobi theory,
Right, right.
and that point in phase space doesn't even move,
Exactly, right.
and yet
No,
it
no,
has the
no.
whole dynamics of the world in it.
It's absolutely, and also, and Hamilton Jacobi theory is sort of the pinnacle of this. It's so beautiful,
Yeah.
and it's so seductive in that way. And you really have to sort of hang on to your seat and say, yeah, this aesthetic reaction I'm having is not is not necessarily good grounds for believing what's true or false about the world. But that's right. That's right.
Yeah.
Howland Jacobi theory is the is the most extreme example of something like that.
Yeah.
Right.
Yeah. So back to quantum mechanics from classical mechanics and this idea of the equipment, the
Right.
instruments, and the people all themselves being made up of particles described by quantum mechanics, and therefore they themselves in aggregate should be described quantum mechanically.
Right.
The big headache for a long time has been to describe how that piece of equipment, when it encounters, say, an electron that's in a mixture, or in technical language, a superposition of being here and there with some probability dictated by the mathematics of quantum physics, how is it that the instrument, when it measures the position of that particle, gets one definite result?
Right.
Because in quantum mechanics, this idea of eliminating one of the possibilities is incompatible with the dynamical equations, the
Right.
Schrodinger equation.
Exactly right.
So the
So
so-called measurement problem. So this has, in some sense, been a wrench in the works is probably not the right metaphor here,
it's not a
but it,
bad metaphor.
all right, then we'll run with it. Well, you can't really run with that's a different metaphor with it, but
You
anyway, I'm
shouldn't
not going
run
to
with
run.
a scissors, right?
Yeah, exactly, exactly. So this has been a headache for a long, long time.
Right.
And look, I remember when I first came to Columbia. You probably don't remember this, but we met for lunch, I think at the faculty house or something like that. And we were chatting. You nonchalantly said, "So, what do you think about the quantum measurement problem?" And I just sort of said, "Oh, well, it's a many worlds interpretation, of course,
Right. Right.
yeah."
Right.
And then for 3 or 4 hours,
Right.
you beat on me,
I'm,
and I
I'm
left that
sorry.
lunch. I left that lunch being, oh my gosh, I'm far less certain than I was of things before, because like many physicists, I had not really interrogated this approach deeply enough to encounter the kinds of issues that you and your colleagues in the foundations had been
Right.
talking about for a long time. So
Right.
maybe you can just give us a sense of the
Yeah.
measurement problem from your perspective, and
Yeah.
then maybe we can just walk through some of the approaches that are
Good.
on the table.
Good. So I think you set it up pretty nicely in what you said. What's common to everybody is that at least subatomic particles can be in these strange situations which people call superpositions, say of being located at this point or being located at that point. This superposition, it is, if you think it through, it's not right to think of this superposition as a case where it's either at this point or at that point, but we just don't know. There's also things wrong with thinking of it naively as being at both points. There's definitely a lot wrong with thinking of it as being at neither point. And the puzzle here is, but wait a minute, that sort of exhausts the logical possibilities. Okay, if location is the right way to talk about it at all. So this is a puzzle, but um, um, maybe one wants to say, well, the subatomic world is just weird, and that's all there is to it. What's called the measurement problem is this: if you ask the mathematics of quantum mechanics, if you suppose that everything can be described quantum mechanically, not only these particles, but everything that large collections of these particles produce, measuring instruments, human beings, universities, blah, blah, blah. All of these are in some principled sense quantum mechanical objects because they're just aggregates of these subatomic particles, which everybody agrees are quantum mechanical. If you take a view like this seriously, which is exactly what Bohr cautioned us not to do, okay, but if you really want to develop a consistent description of the whole world, it turns out that it's not that hard to ask yourself, look, suppose I had a device with a pointer on it, a macroscopic device, which when I place the particle here and I turn the machine on, the pointer always swings to there. And when I place the particle here and turn the machine on, the pointer always swings to there. Good. You can ask the quantum mechanical equations of motion, what would happen to such a pointer if when I turned it on, the particle was not here and not here, but in one of these quantum mechanical superpositions of being here and there? Um, and it turns out that the quantum mechanical equations of motion give a very straightforward answer. The pointer will go into a superposition of pointing this way and pointing that way, a superposition which is what physicists call entangled with the superposition of the particle itself. Forget about what that means for the moment, but the pointer itself will go into a superposition. That is, the pointer itself will go into a state where there is no fact of the matter about where it's located, where asking whether the pointer is pointing to the right or to the left is like asking about the marital status of the number 5. Or something like that. It's the kind of thing that philosophers refer to as a category mistake. Okay, by simply raising the question, you're showing that you don't know what's going on. No, the number 5 doesn't have a marital status. Marital status is not the kind of concept that applies to the number 5. Okay, so what you want to do in one way or another in solving the measurement. So people say, look, maybe elementary particles behave in some crazy way, but I know damn well from everyday laboratory experience what happens when I turn my measuring device on. Sometimes the pointer goes this way, sometimes it goes that way. Nothing else ever happens. Okay. I never see it being vague or undefined, or I don't even know what that would look like, but I don't need to know what it would look like because I know it won't, I know it doesn't happen. When I turn on these measuring devices, sometimes the pointer points this way, sometimes the pointer points that way, with fixed probabilities that I can predict from the initial state of the particle that I'm measuring. That's what happens. How is it? That seems to be a direct violation of the quantum mechanical equations of motion. How is it, if we want to take seriously that we have a single model for all of reality, us and the subatomic particles and so on, we've got to figure out how to get rid of this problem. And there's a famous quote from John Bell, um, which I think is very helpful here, which he says, look, there are two possibilities. One is the equations of motion, which gave us this result about the pointer, are just wrong. They give us good results about the way subatomic particles behave, but when you put a lot of these particles together, there must be some kind of an effect which is too weak to see on the level of individual subatomic particles, but somehow builds up when you've got a bunch of them put together in a pointer, that the equations which led to the prediction that the pointer is going to end up in a superposition of being here and here are just wrong. Okay. And we have to modify them somehow. Okay. And in the 1980s, such a modification was actually proposed by 3 Italian physicists named Gherardi, Rimini, and Weber. Um, and they very cleverly thought of a way of modifying the equations whose effects would be almost completely unobservable on the level of the behavior of individual or small numbers of subatomic particles, but which would build up in the appropriate way when you have something big like a pointer, and make it the case that we wouldn't get in the end a superposition of 2 pointer positions. We'd get a probabilistic evolution in which we sometimes ended up with a pointer pointing here and other times ended up with a pointer pointing there. So that's one of the these are called collapse models. Um, um, Even back in the 1920s and 30s, there were people who going against Bohr's advice wanted to go native, wanted to develop a single language for everything, wanted to sort of give its due to the observation that if these subatomic particles are quantum mechanical, then we must be quantum mechanical too, because we're nothing but aggregates of these subatomic particles. So people like von Neumann, in his famous book, The Mathematical Foundations of Quantum Mechanics, does say, look, maybe the way to solve this problem is to introduce a violation of the Schrodinger equation, which he called the collapse postulate. Unfortunately, his proposal for how to introduce it was to say that these violations of the Schrodinger equation occur when you do a measurement, okay? And locutions like when you do a measurement are just not nearly, don't have anything like the precision or disambiguity that we expect of propositions that occur in a fundamental physical theory. So that looked like a ridiculous theory. The achievement of Ghirardi and Ramini and Weber many, many decades later in the 1980s was to come up with a precise formulation of a claim like this that didn't involve any words like measurement. But
Huge
it had the
speculation. Yeah.
consequences that von Neumann hoped for.
But
So,
when you just one
sure.
question on that, David. I mean, if GRW had presented their ideas at the 1927 Solvay conference,
Right,
for instance,
right.
I know no one can really answer, but do you think Bohr would have been open to at
It's a
least the
good
possibility?
question. Bohr was, Bohr is such I must say that, you play this parlor game. Which historical figure would you most like to have over for dinner? Okay. Um, if you ask me, it's Bohr. Okay, for me.
For me, it's Shakespeare, but
I, I don't know what the deal was with Bohr. There
yeah.
was there was the guy. What's clear is the guy must have been one of the most charismatic human beings that anybody has ever met,
Mhm.
that has ever walked on the face of the earth, because the smartest people in the world at that time worshipped him.
Yeah.
Okay, really, he was kind of a Gurdjieff kind of figure, or something like that. He was this guru, and the funny thing is, and he shares this with charismatic mystics like Gurdjieff. You go and read what was supposed to be his wisdom, you can't make sense of it. Okay, you can't even figure out if two of the pages were reversed. Okay, but everyone who took a walk in the woods with him for a half an hour, their life was changed. Okay. And these were the smartest people in the world. So Bohr is an extremely mysterious figure for me. I don't know. I don't know what he would have said. I do think he was very invested in the idea that Einstein had left physics with a whole radically new vision. Okay, maybe the vision of geometrizing all of physics or something, and that Bohr felt he needed to leave
Mm.
physics with a similarly radical and similarly sweeping vision, and he was very, very invested in that.
Mm.
Certainly, I don't know what Bohr would have thought of GRW, but we do know what Bohr would have thought of what Bohr thought
Many
of the many
worlds.
worlds
Yeah,
interpretation
sure.
that you mentioned. And he was without offering any reasons, not only dismissive of it, but apparently irritated by it and angered by it. So
Yeah. Can you tell the audience just a little bit of Many Worlds, just to
yeah,
bring
yeah.
everybody up?
So let me well, so
Yeah,
let me
yeah,
get to so let
sure.
me get to it through this Bell remark.
Yeah.
So Bell said very nicely, look, what the measurement problem is telling us about quantum mechanics is that either the equations of motion are wrong or they're incomplete. Okay. Um, um, the wrong alternative is the one that is the alternative of thinking that they're wrong is the one we just explored, with these collapse theories like GRW. The equations of motion are simply wrong. We have to amend them a little bit so as not to mess up any of the predictions they make, which we know are true, but to also make it the case that the pointer does choose one position or the other once we do the measurement. Good. There's a second alternative. They're incomplete. Okay. Um, Here's an example of that. This is Bohm's famous theory. Look, it's true what the quantum mechanical equations of motion say in a situation like this. The quantum mechanical wave function of the pointer does show a bump corresponding to the pointer pointing this way and a bump corresponding to the pointer pointing that way. But that's okay, because the wave function turns out not to be a complete description of the state of a system like this. There's some additional fact, some little X that you put on one of the bumps in the wave function and not the other, which indicates where the pointer really is. Okay. Now, if these X's exist, you have to have a serious physical theory of them. You have to tell everybody what their equations of motion are, so on and so forth. These X's are sometimes referred to in the literature as hidden variables, although that's an awkward name because in the case of the pointer, it's obvious that the X's are the things that we actually see. Okay. But anyway, there is a famous example of a theory like this. Bohm's version of quantum mechanics, Bohm's hidden variable theory, or what's sometimes called Bohmian mechanics, where he does have these X's, okay, and where you can see, aha, I see, even though the wave function does what the equations say it's going to do, the X is here and not here, okay, and that's what it is about the state of the world that determines that we see the pointer there and not there. Good. So those are the two alternatives that Bell mentioned. Okay.
I don't mean to take you off course, so hold for half a second, just because it's interesting to note that a version of that theory was presented at the Solvay
Yes, that's
conference
right. This is
by
the
Troy.
Broy. Yes. Very. Yeah. Thank you for reminding me. That's right, and it is a good question. Unfortunately, De Broglie didn't know how to. De Broglie folded way too quickly. Okay, under criticism, which it would
By
have been.
Pauly. I think it was
That's
Pauly.
right, by Pal, exactly.
Yeah.
Which in hindsight, it would have been easy to respond to. Okay. So he folded very, very quickly. And so presumably Bohr didn't need to get into the act. Okay. But you're right. A theory like a sort of primitive preliminary version of a theory like that was presented at that Solvay conference. It got dispensed with very quickly. In hindsight, it got dispensed with much, much too quickly.
Yeah.
But right, that's what happened to that. Good. Then there's a third alternative which has been pursued, which Bell doesn't mention. Okay, which is to say, no, I want to have my cake and eat it too. That is, the quantum mechanical wave function is a complete description of the world, and the Schrodinger equation is exactly true. Okay. And now the question is going to be, well, then how do you explain the fact that in the laboratory, we always see the pointer pointing either this way or that way? We never see some combination of the two, whatever that might mean. Um, 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 that's what we see. The idea is, you haven't gone far enough in applying the Schrodinger equation here. Apply it also to you looking at the pointer. You're gonna there's now gonna be a branch of the superposition in which you see the pointer pointing this way, and a branch of the superposition in which you see the pointer pointing that way. And it's easy to derive from the equations of motion that, as it were, the person in this branch won't be aware of the existence of the person in the other branch, yada, yada, yada. So maybe, in fact, we didn't have to go to all this trouble. Okay. We didn't have to think about what might be wrong with the Schrodinger equation or what might be incomplete about the wave function. Turns out the Schrodinger equation is not wrong, not even a little wrong. And the wave function is not incomplete at all, okay? Rather, what quantum mechanics is depicting is a universe that keeps on splitting into multiple copies of itself every time something like an experiment occurs or something like an observation occurs. Um, um, and that's the picture of the world. This is a way of confronting the measurement problem, which has a very understandable appeal to lots of theoretical physicists, and which did, as you described of yourself. And I take it that a big part of the appeal is this is the way of solving the measurement problem that does the least violence, indeed, that does no violence at all to the original mathematical structure of quantum mechanics. The idea here was the solution to the measurement problem is not to modify either the equations of motion or the description of the world. The solution to the measurement problem is to realize that if you just calm down for a minute and take a breath, there was never a problem in the first place. Okay. Quantum mechanics, as originally presented, was completely adequate to this. It's just that following quantum mechanics all the way out to its logical conclusions was something that not enough people had the stomach for, as it were. Okay. Because it was going to commit you to the world splitting into lots of different branches where there are multiple yous having different destinies, seeing different outcomes to experiments, blah, 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 blah. I think what I must have spent several hours browbeating you about on the occasion you describe is that I've thought for a long time that the many worlds interpretation is not up to the task of saying why we see the frequencies of various different experimental outcomes that we do. On this theory, everything always happens. Period. End of story. It's like, in order to make sense of it, suppose you're talking to an amoeba that's about to split into two amoebas, and you say, "Tell me, what do you think the chances are that you're going to end up on the right?" Okay. It seems to me the right thing for the amoeba to say is, "Gee, I don't even understand the question." I mean, the first thing to say is, "I'm not sure what you mean by I here." Okay. I'm going to be related to the one on the right in very much the same way that I'm related to the one on the left. They're both my descendants. And the situation is completely deterministic. There's going to be one on the left, there's going to be one on the right. I just don't understand where talk about the probability that I'm going to be the one on the right can even get its foot in the door here. This is a long story. There
Yeah.
have been lots of really ingenious attempts from which we've learned a lot to answer a challenge like this. I don't think any of these attempts, however ingenious, have been successful. And as more time goes by, I'm more and more convinced that I can see reasons why they can't be successful.
But just to say, I mean, there are many, not many, but there are a handful of people who've spent a lot of time on this very
Absolutely.
problem. The whole group at Oxford, many of them
Exactly.
expanded.
Exactly. Very people who I enormously respect,
Yeah,
and
because I mean,
indeed people who I've learned an enormous amount from in having these debates. And
yeah,
not only have we learned a lot about quantum mechanics from these debates, we've learned a lot about the basic nature of probability from these debates. There's this will sidetrack us for 5 minutes, but whenever I start a philosophy of science class, I usually find it good to get the students interested, to sort of convince them in some simple way that there's a locution they use 100 times every day and that they don't have a clue what it means, in fact. And a very easy way to do that is to start with the problem of probability. Suppose a Martian comes down to Earth and masters all of the sort of indicative locutions in English. He knows what it means to say there's a chair here. He knows what it means to say the coin landed heads. He knows what it means to say the coin landed tails, blah, blah, blah. Um, um, but the Martian is puzzled about probabilistic locutions. And he comes to you one day and he says, sometimes people say the coin will land heads. And I know how to decide whether this prediction turned out to be true or false. And sometimes they say it'll land tails. But on other occasions, they say the probability is 60% that the coin will land heads. Could you tell me what that means? I don't seem to have the vocabulary there. And there's an interesting conversation in the class, which usually goes in roughly the same way, where somebody will say, well, it means that if you flip it 10 times, 6 of them will be heads. And you say, really? I mean, if you added to the end of your sentence for sure or with certainty, would it still be true? And student says, oh, you're right. I'm sorry. I don't mean for sure 6 of them will be heads. I mean, probably 6 of them will be heads. And then you say, no, but you don't want to say that because you're using a term, you're using the term that you're defining in the definition. Your definition is going to be worthless. It's going to be circular. Goes on from there. Somebody suggests if you flip it an infinite number of times, 60% of them will be heads. Then you have to point out a couple of things, one of which is I'm not sure what 60% of infinity actually means. Then somebody will start talking about limits. That's wrong too. And after 15 minutes of conversation, you have the class convinced that they had no clue what they've been talking about all their lives when they talk about probability. So this debate about whether probabilities can manifest themselves properly in the many worlds interpretation has been one from which there's been a wonderful side benefit that questions have been raised about what probability means that turn out to have been much sharper and much more informative than questions that had been asked before over hundreds of years of debate about this.
Yeah.
So,
Yeah.
yes, it's by all means been a great thing. I don't think they've succeeded in defending the many worlds interpretation, but these are people of very admirable, intelligence and creativity. And this is a discussion from which we've learned a lot.
And my understanding, and again, correct me if I'm wrong, is that none of them have capitulated on
That's
this.
true. That look, if you study foundations of quantum mechanics, something you learn is that a very important engine of progress in physics and in lots of fundamental subjects is that people die. Because people, once they've gotten deeply entrenched in something, have trouble giving it up, and one has to realize this about oneself as well, and you become very impressed with the fact, especially as you get older, that these are decisions that are going to be made by future generations, after you're dead. Okay. And that's what's going to happen. Yes. People haven't moved very
Could
much.
you be entrenched in the failure of many worlds?
Um, of course I could be. I mean, I don't know what to say. I don't think it is, and you see it in philosophy, and one will begin to see it in physics because there's going to be such a problem of underdetermination. Um, you see this curious phenomenon of intellectual disagreements that don't involve anything that it would be appropriate to call dishonesty, but that people really do think themselves into trenches, become entrenched, and it's hard to see one's way out. There's a um, a political philosopher I like, and he says, "Look, I grew up in this in this family that was involved in the labor movement, so on and so forth. I know, or I am willing to accept, that if I had grown up in a different kind of family with the same, basic cognitive apparatus, I would have reached different political conclusions about what's right and what's wrong. And I honestly don't know what to do with that knowledge. I mean, I think the way to reconcile yourself to this, so could I be entrenched? Of course I could be entrenched. I think what you have to tell, the story you have to tell yourself, which I think is a true story, is that the kind of service you're doing to the advancement of knowledge is to present the best arguments you can come up with for whatever trench you happen to have landed in. And then those arguments will be available to people in the future who are going to make less personally invested decisions on what turns out to be right and what turns out to be wrong. So
Yeah.
I think my sense in the community of foundations of quantum mechanics, where there are debates about these sorts of things, is no, we see what we're doing. We see that we're entrenched. Actually, that sort of entrenchment could be conceived of as something that furthers the aims of knowledge. Okay, not our personal knowledge, because we're stuck wherever we're stuck, but it produces the most vigorous kind of debate you can have. It produces the best available defenses of these various positions, and then our grandchildren will figure this out.
And I think the important thing to stress there, which is a point that you made, there's nothing nefarious, there's no malfeasance.
Right,
It's completely. I mean, I don't know of any colleague who doesn't work on what they work on
right,
and hold the views that they hold because they are deeply committed to advancing truth.
right, right,
That's the only thing that they're
right,
committed to.
right, right,
And so because sometimes I find it kind of sickening a little bit, but online you see these conversations about groups of physicists that are somehow hiding the truth about the
right,
failure,
right,
whether it's string theory failed, which is not, hiding the truth
right,
because they're too entrenched personally to
right.
allow the reality. And it's just such nonsense
I think
because we're
that's
all,
right.
yeah,
I
yeah.
think
So,
that's right.
but anyway, putting all that to the side, GRW theory, as I understand it, is the one approach, or at least in principle, is experimentally
Correct,
distinguishable
correct.
from, say, the de Broglie-Bohm approach, where the wave function does a little extra work than it
Correct.
does in the conventional approach, or many worlds, where it's just the vanilla version of quantum mechanics,
Right,
properly thought
right.
about, really taking it
Sidney
seriously.
Coleman, Sidney Coleman used to call Everett quantum mechanics in your face,
Yeah. Yeah.
which I thought was very nice and very apt. Yeah.
No, I agree. In fact, I was working on a little thing for like 6 months on trying to work out an approach to the measurement problem, and it was in Sydney's talk, and
Right, right,
I did not know. I don't know if you remember how he had this approach of trying to find eigenfunctions of the
right,
uh, yeah, and the operator that actually was
right,
describing the instrument itself as the physical system. But yes, I think quantum mechanics in your face is a great way of describing it.
right.
But do you hold out any hope, any realistic hope of testing GRW theory?
I mean, compared to what? Compared to string theory? I
Here
mean,
we go.
I mean, yeah. Look, um, something that has, you know, when GRW theory was first proposed, it was everybody thought that if there was ever going to be a test of it, it was going to be hundreds of years away. Then there were the development of these squid devices
I
and
remember. Yeah.
so on. Experimentalists have been just really, really clever. Also, people realized that in experiments that were looking for proton decay, where you had these huge tunnels full of water, huge
Yes.
wells mine shafts full of water, and you lined the whole mine shaft with these very sensitive photon detectors. It turned out that put limits on the GRW theory. That is, indeed, it's the case. When you write down the GRW theory, you have to choose new natural constants, which are going to tell you the frequency of these collapses and how violent the collapses are, and so on and so forth. Now, it just so happens that the first version of this that was written down by GRW has already been ruled out by experiment. Okay. These proton decay experiments, it turns out, have ruled them out. You can even rule them out with some squid experiments. The worry is that they have a lot of wiggle room as to where to set these constants, but the wiggle room isn't infinite. So I don't know what to say. I think that it's conceivable, that over the course of the next century or something like that, experiments could take us to a place where the GRW theory no longer looks plausible. It's not logically ruled out, but you're pushing the collapse into places where there are other reasons for thinking that it's not plausible that it is. So if the question is, if the question is anything going to strictly logically rule it in or out? No, I doubt it. But I think that with the help of experiments, it could become a more or less plausible
Right.
proposal than it is now. Yeah.
Yeah. And the other question that comes to mind, of course, in all of this, especially when you start to talk about many worlds, where, again, if it were to succeed, you'd have this whole question of, who am I if I
Right.
am each of these branches? So somehow my consciousness is playing some kind of role in our discussion of this approach to quantum mechanics. Eugene Wigner was one of the people who pushed hard on the idea that consciousness was part of the issue here
Right.
and needed to be taken into account if you're going to solve this measurement problem.
Right.
Where do you come?
Well, so there's several things to say about that. The way Wigner did it, there's lots of debate in philosophy today. I mean, there's a whole thriving field of so-called philosophy of mind, um, um, which is centered on questions about the relationship between the physical and the mental. Okay. But there's a particular attitude towards the relationship between the physical and the mental, which people refer to as interactive dualism or Cartesian dualism, which I think there's a pretty wide consensus nowadays is the wrong way to go. Okay. This is the kind of view that Descartes had, that mind and matter are utterly separate things, okay, but that it's also the case that mind can influence the evolution of matter, okay. Indeed, Descartes famously thought that you could locate in space the point of interaction between mind and matter that was in the pineal gland in the human brain. Why he thought, I'm sure he had reasons for thinking that it was the pineal gland. I don't remember what they were. But um, people like Descartes thought not only were these two separate metaphysical realms of being, but the mental part could affect the physical part. It goes without saying that, of course, the physical part can affect the mental part. If something happens across the room that I see, that affects my mental state. Okay. What's more surprising is the thought that things that originate in the mental space can end up affecting the physical space. That's that's what one is thinking in very old-fashioned conceptions of freedom of the will, or something like that. That there's something that could originate on the mental level, like my decision to raise my arm, and then my arm goes up. The trouble with interactive dualism is that, to the extent that you want to defend interactive dualism, it looks like your attitude towards physics is not a neutral one. Your attitude toward physics must be that physics as we understand it is wrong. Okay.
Yeah, exactly.
Because there are physical events that don't have thoroughly physical explanations. Okay. Um, Good. For that reason, most people nowadays are embarrassed to be old fashioned interactive dualists. Wigner's thought was something like the following, and it's a lovely thought. I also think it's a crazy thought and an intellectually irresponsible thought, but you could see why somebody would get so excited. Wigner's thought was, look at this. In quantum mechanics, we have to get the wave function to do something, this collapse, that the physical equations of motion are not going to get it to do. Okay. So we've thought, for the reasons I was just saying, that being an interactive dualist means you're denying that the whole physical project is correct. Okay. Wigner thought, look how this turns everything upside down. We've got this job that needs to get done, namely collapsing the wave function, which it looks like physics can't do. Okay. We need an interactively dualist mind to do this for us. So look how this turns the tables on the old debate. It's not only that the existence of such a mind is no longer hostile to the physical project, it's necessary to the physical project. The physical project can't achieve the completeness it wants without this thing. So he has this new, beautiful, unprecedented definition of the distinction between the mental and the physical. What it is to be a physical object, to be an isolated physical object, is to obey the Schrodinger equation. What it means for mind to be involved somewhere is that there are various very specific violations of the Schrodinger equation in these collapses. Okay. Like I say, one can see why Wigner was thrilled about this. I remember when I was a young physics student seeing Wigner talk. You're probably too young to have
Yeah,
overlapped with
didn't
Wigner.
overlap.
I
Yeah.
saw Wigner give a talk where he said, literally, he said, in his opinion, dogs could probably produce collapses, but mice probably couldn't. Okay.
Wow.
And I remember saying to myself, this is not good. Okay. This is not a good way to do physics. Okay. That is, he was running into exactly the same problem as von Neumann had run into with the vagueness of a word like measurement. But here, the vagueness was in the meaning of a word like conscious. Okay. Conscious entities could produce collapses. Purely physical entities couldn't produce collapses. And before you know it, the guy's saying that dogs can produce collapses, but mice can't. And you suddenly realized, you come down from this euphoria of thinking, oh my God, consciousness is the solution to everything, and you suddenly realize that it's gotten you nowhere. That you're right where you were with von Neumann. You've got these vague words in von Neumann's case, measurement; in Wigner's case, consciousness. You don't know what they mean. You don't have a clue how to begin to incorporate them into anything that looks like a serious physical theory.
Yeah.
So it was. I guess I like to think of it this way. It does show why somebody like me, who, as I said a long time ago, whose sort of basic interests were always in the philosophical direction, it shows why somebody like me would become so fascinated with the foundational problems of quantum mechanics. It shows how much was at stake in these problems. You step back from this Wigner episode for a moment, okay, and you say, how did we get here? What the hell happened here? Well, the story was you got these guys minding their own business, doing their work competently as physicists, trying to figure out how rocks work. Okay, that's all they're trying to do. Nothing fancy, nothing. I mean, nothing like what literary people were trying to do, right? They're just trying to figure out how rocks work, and they're doing their jobs competently and honestly and correctly. And you fast forward 50 years, and people are talking about consciousness, and this somehow got wrapped up in this, and it's an indicator that something terribly deep is at stake here.
Yeah.
Okay.
Yeah.
The whole integrity, the whole sustainability of the project of physics as originally conceived is at stake here. Okay. So I think this is a ridiculous episode in a way, but I also cherish it because
Yeah.
it's indicative of how much is at stake here.
No, I totally agree. A question that this also leads me to ask: many of the papers and foundations of quantum mechanics, by no means all, but many start with the formalism of non-relativistic, gravity-free quantum mechanics,
Right.
and in that setup, do a lot of the analysis that
Right.
we spent this whole discussion talking about.
Right.
Do you think that moving to relativistic, which means special relativistic or general relativistic, including gravity into the story, Penrose has, famously argued that he thinks gravity is intimately bound up with some of the issues that we're talking about here. Does that resonate with you?
I mean, it's hard to tell in advance which approaches are gonna yield fruit. And this harks back a little bit to our discussion about being entrenched in various kinds of views. You do what you're good at, and you contribute where you think you're going to be able to make a contribution. I certainly don't think it's crazy that people start with non-relativistic quantum mechanics, just as it's not crazy that when people talk about issues like the direction of time or something, they start with Newtonian mechanics, okay? Even though nobody believes Newtonian mechanics anymore. Why do they start with Newtonian mechanics? Because this phenomenon of the time reversibility of the fundamental laws comes up in Newtonian mechanics in much the way it comes up in our most advanced physical theories. And there's a thought that since Newtonian mechanics is the simplest of these, if we first get a handle on it there, okay, that may be of huge help to seeing how this is going to go. Whatever kind of handle on it we get on there may be translatable without too much trouble into the language of more contemporary, more advanced
Yeah.
physical theories. Now, you hope that's the case. Sometimes it is. Sometimes it's not. Okay. Um, 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 in the case of statistical mechanics, for example, I think I still, in my courses on foundations of statistical mechanics and the direction of time, I start out with Newtonian mechanics. I think that works well. On the other hand, something interesting about the GRW theory we were just discussing is that it's a theory that has real stochastic evolution built into its dynamics. You might wonder whether these stochasticities have any interesting relationship to the foundations of statistical mechanics, and I think they very well could. Okay. I think if GRW theory turned out to be true, it would change our picture of the foundations of statistical mechanics. So, in that sense, a lot of the work in the Newtonian context would turn out to be irrelevant. Okay. Or irrelevant is too strong a word. It would turn out to be not as directly relevant as
Yeah.
we might have hoped. So,
Right.
look, there are various approaches to these things. I remember a time when I was a young PhD in physics, and I was interested in the measurement problem. And almost every physicist I met would tell me, "You're an idiot because you don't understand that quantum field theory solves all these problems immediately." Okay, this just turned out to be wrong. Okay, completely wrong. Okay, so one doesn't know. One always wants to assure oneself, or assure oneself is too strong a word. One always works on these simpler models in the hope that whatever you learn from those simple models is going to be applicable to more advanced ones. Sometimes that works out, sometimes it doesn't. More usually, it works out to a greater or lesser degree. Um, I don't know what to say. Another problem with, say, suppose you want to do foundations of quantum mechanics in the context of relativistic quantum field theories. The trouble is, so you have a scheme like GRW, or you have a scheme like Bohm for solving the measurement problem in non-relativistic quantum mechanics. The trouble is that the minute you get to relativistic quantum field theories, you're not given a basic mathematical apparatus which is consistent in the way that non-relativistic quantum mechanics is. Okay, and there's been a big struggle to try to adapt these mechanisms like we discover in GRW theory or Bohmian mechanics to quantum field theory. And a lot of the people who work on that, I've done some work on that myself too, say, look, here's the deal. You can take this a certain distance, okay? But eventually, the theory you're starting with that you're supposed to modify in this way isn't a mathematically well-behaved theory in the first place, okay? And these people often say, and I think they're sort of right, if you were to give me tomorrow a clear and internally consistent mathematical formulation of quantum field theory, I bet you I could Bohmize it for you, or I could GRWize it for you in 2 weeks. Okay,
Huh.
so it goes both
I mean,
ways.
I gather this has been tried, and I don't want to get too technical for the audience, but I mean, I've taught quantum field theory many times, and almost never do I ever introduce a wave function in
Right,
relativistic
right,
quantum
right,
field
right,
theory.
right, right.
We use it's sort of like we discussed those two students whose mind got blown when you introduced phase space.
Right,
We introduced a different representation of the quantum ingredients, in Fox space, getting a little
right,
bit technical and things of that
right.
sort. But you could, and people, of course, have written down quantum field theory where there is a wave functional of the
Correct,
fields, and
correct.
and
I
I
mean, for
gather people must have
fermions, it's a
tried.
little more complicated than for bosons, but
Yeah,
you could, but that's right. You can write down this wave functional. Okay. You can play this game with the wave functional, but there are still problems. All the mathematical problems in the fundamental formulation
yeah,
of the quantum field theory are going to still be there in this wave functional form. But yes, when we try to do, say, a GRW theory for quantum field theories, of course the first thing we do is write it down in this wave functional formalism and apply a GRW theory to that. Apply a sort of GRW mechanism to that. But um, there, you know, I don't know how to put this succinctly. There's a lot going on. Am I glad that there are people who are trying to talk about the measurement problem, starting with quantum field theory and even starting with string theory or something like that? Of course, I'm glad. Okay, we're going to find stuff out that's interesting and useful. But if the question is, do I think it's obviously bankrupt to start with non-relativistic quantum mechanics? No.
yeah,
I think that's a strategy that's proven very valuable in physics time after time.
yeah, yeah, for sure. And so when you say are advising students today, where do you instruct them is the more fruitful place to go, or do you not even care about future I mean, what's the state of the
So here,
field in terms of
it's
some
a
of these
really
ideas?
lucky thing I mean, the humanities in general and philosophy in particular has been decimated in recent years in terms of the number of jobs available, so on. We just happen to be very lucky in the little corner of philosophy that people refer to as foundations of physics. That because the field, this goes back to the historical discussion we had a little while ago. Um, um, the field has sort of reawakened
Mhm.
after a century of slumber, okay, after a century of dogmatic slumber, like Kant said, when everyone was told that this is not among the proper uses of physics to try to do metaphysics with it, to try to do really kind of foundational investigations with it. This has reawakened. I think that it's fair to say that between, say, 1980 and 2000, for the people who were paying attention, okay, for the people who were serious about this doesn't include everyone, as you pointed out, it doesn't include the whole physics community, but for people who I think were paying attention to this stuff in a serious way, there was a kind of sea change. The measurement problem was not, as Bohr conceived of it, our encounter with the limits of scientific inquiry. Okay. For Bohr, this was not a problem to be solved. This was a problem to be bowed down before, or something like this. This was not an ordinary scientific problem. This was an encounter with the limits of the possibility of scientific inquiry per se. Okay. I think what happened between the year two the like 1980s and around 2000 is that it was demonstrated to the satisfaction of everybody who was paying attention that no, this is a scientific problem. Okay, that is paradoxically the job that philosophers, I think, succeeded in doing, or mostly philosophers. There were physicists involved in this too, people like Shelley Goldstein, who you mentioned, and
Yeah.
so on. But the job that a group of people, many of whom were philosophers, did, well, the job that this group did was to say, by the way, this is not a philosophical problem. This is a scientific problem. Okay, and what we can contribute here as philosophers is the ability to cleanly recognize the distinction between something that's a philosophical problem and something that's a scientific problem. And we have news for you. This is a scientific problem. Okay. I think that case was successfully made by around 2000 to, like I say, anybody who was paying attention. And this seemed like one of those rare occasions that excites people a lot where philosophy actually got something useful
Yeah.
done. Okay. There's a lovely line by Bertrand Russell. Somebody's asking him to respond to the impression that philosophy never does anybody any good. Philosophy never accomplishes anything. And Russell said, of course it looks that way, because every time philosophy accomplishes something, its name is changed to that of a science.
Mhm.
Okay, that's what happened in foundations of mathematics, blah blah. If philosophy accomplishes something and they say it's not philosophy, this is science, good. That's sort of what happened here. It was one of these Bertrand Russell type occasions when philosophy actually seemed to accomplish something, philosophy actually seemed to learn something. This produced a lot of excitement in philosophy departments, and it became the case that every department, that it used to be the case that no more than 1 in 20 philosophy departments in the United States had somebody working on foundations of physics. Now everybody wants one. Okay. So now, happily, within philosophy, if you have a good student, if you have a talented student, the best advice is work on whatever interests you. I promise you're going to get a job.
Yeah.
That's a very happy situation to be in. How long it will last, I don't know. The time will come when all the departments who do want to have somebody doing this has somebody doing this, and then things will drop off. But at the moment, we're in the very happy situation where the best advice to give a really talented student is follow your interests. It'll be okay.
Well, that's absolutely wonderful. It's also a great spot for us to conclude this conversation. But before you go, I want to have you on record as agreeing. There are two other conversations that I want to have with you. One's on quantum entanglement, and the other's on the arrow of time.
I'd
If,
love that. I'd love that, Brian.
so we can do a part two and a part three at
Sounds
some point,
great.
so we don't overburden this one. So
Sounds
again,
great.
fascinating conversation. Thank you so much for the time and for joining us, David. And I look forward to
Thank you for
continuing
having
the
me.
conversation going forward.
Me too. Thank you for having me, Brian. Nice to see you.